We start here talking about gases. As the first state of matter, we have gases, liquids, and solids, but gases give an opportunity to focus on just the molecules, just the atoms. Because we make certain assumptions about gases, because they're mostly true under our environmental conditions, about 1 atmosphere pressure and about temperatures of, 0 degrees Celsius to 100 degrees Celsius, room temperature type thing, which is often what we talk about. So gases give an opportunity to focus on the properties and the actions of individual particles. And we talk about this as kinetic molecular theory. Kinetic molecular theory, or as the cool kids call it, KMT, is a very conceptual idea we need to understand. And so we talk about these particles in an ideal or perfect situation. We call these ideal gases. Not all gases are ideal. In fact, probably no gases are ideal. By talking about them as ideal gases and making assumptions, we can talk about them in this conceptual, theoretical way. Now, most gases do not deviate from the ideal. In other words, and for our purposes, there's nothing wrong with considering them ideal. Their properties, we can make predictions, we can do calculations of these ideal gases. But in order to make them ideal, we make 4 assumptions, which may or may not be true. Sometimes they're true, sometimes they're more true than others, sometimes they're not true at all. By the way, when they're not true at all, we call them real gases. But as ideal gases, we make 4 assumptions. The first assumption is that particles, these gas particles, or either atoms or molecules, are so small that in a sample of gas, the particles themselves take up 0 space. The entire amount, the volume of the gas, the sample, is empty space. The particles are so small and they're so far apart that really the volume they do occupy is insignificant. It's incalculable compared to the total volume. So we assume they take no space and the entire volume of the sample is available for these particles to move around in. The second assumption we make is that particles are in constant motion. Ideal gases, constant motion. The particles are always moving. The third assumption is that gas particles do not affect each other. As they pass by each other, they don't even know they're there. They don't attract each other, they don't repel each other. All they do is sometimes, yes, they collide and they bounce off each other in what we call elastic collisions, where no energy is lost to the surroundings. In these collisions, the energy may be transferred between one particle and another, but no energy is lost, elastic collisions. But as they're going past each other, unless they hit each other, or unless they hit the sides of the container, the particles are not influenced or affected by anything else in the sample. So they keep going in a straight line until they hit something. And the fourth assumption we make is that kinetic energy of a particle is proportional to the temperature of the particle. It's going to be very important in our calculations. But in other words, what that really means is that as temperature goes up, the kinetic energy increases. And this leads us to some, again, understanding of how these particles behave. Keep in mind, this is an ideal gas situation. Gases aren't always ideal. Sometimes sometimes we can't ignore that the particles are so small. We can't ignore the size they take up. When the pressure is very high, they take up a volume, and we can't assume that the entire space is available for them to move. And when the temperature of the particle is low, we can't assume that they do not affect each other. When it's low, they start influencing each other. They don't fly by each other anymore. Those are the conditions of real gases, high pressure or low temperature. But as ideal gases, we talk about these things. And so we must consider, as we talk about these particles, you must consider the motion of these particles. You must consider what's going on with an individual particle. As temperature goes up, what happens to a particle in kinetic molecular theory? It gets more energy, it moves faster. As the volume of a system gets larger, while the particles now don't collide as much, they don't hit the sides as much. They have more space to travel. So an ideal gas sample, as in a larger volume, will have a lower pressure. Again, because the particles focus on the motion of the particles, focus on what's going on with the particles when you're talking about kinetic molecular theory. We need to talk about those particles and how these assumptions play a part in their action. If I add more gas to a sample, to a balloon, for example, what's going to happen? Well, now the gas particles are going to collide more often. And in a balloon, that's going to increase the pressure. That means it's going to hit the sides more often. And the balloon is going to get larger because it's exerting more pressure on the side and stretching the balloon until the pressure inside becomes greater than the pressure outside. So when you put air into a balloon or a basketball or any kind of ball, it's going to get larger. We can explain that again because of the motion of these particles in kinetic molecular theory. Focus, especially on your exam, on the kinetic molecular theory. It is critically important that you do this.